Welcome to Miss Lisa's YouTube channel where we talk about all things science and math. Not really, just the ones I want to talk about. And you're wondering why you are looking at the corner of my kitchen. It's because I want this video to be vertical. So, and if I don't let it go vertical for a second, then it wants to flip it horizontal, which wouldn't be the end of the world, but I want it vertical because this is a calculator video and the calculator fits that way on the screen. All right, so this goes with the physics class where we are talking about acceleration, but if you like the way I explained this, then you are more than welcome to join us. What we're going to be doing is I'm going to show you how to do 10 common acceleration problems in physics for high school. So physics problems are just word problems, and what we have to do is get rid of the words because that's what's making it hard. Get rid of everything extra, get it down to the numbers, then find a formula that matches, substitute it in, and get the answer. All right, and we're going to use our calculator to do that. Okay, so our first example problem, number 1, says the velocity of a car increases from 2 meters per second at 1 second to 16 meters per second at 4.5 seconds. What's the car's average acceleration? Okay, oops, sorry, I didn't mean to drift off there. None of the words that matter, we don't care that it's a car, we don't care any of that, we just care about these numbers. And our first number that we're getting, so what I do when I have a word problem like this, any word problem, chemistry, physics, math, is I list my knowns and unknowns over here. I think of a formula that might work, then usually I sing a song, substitute, and then I do the math. Okay, so that's how we're going to do it. They told us that the velocity was started off at 2 meters per second, that the time started out at 1 second, I should have put my second in there, that the velocity ended at 16 meters per second, and my time ended at 4.5 seconds, and what we want is the average acceleration. All right, so the formula for average acceleration is change in velocity over change in time. And that triangle means change or difference. So, excuse me, it's the Greek letter delta. And in science and math, you don't ever have to write change or difference again. This is accepted as the symbol for it. Sorry, I'm getting choked. This is like my 10th video today. And that makes it where I start coughing. Sorry about that. All right, so now to get my change in velocity, I take my final velocity minus my initial velocity, or just the difference in them, and it's 14. And the same thing with the time. That's my final time is 4.5 seconds, minus 1 second is 3.5 seconds. And then this means divide, so 14 divided by 3.5, and I would do that on my calculator, is 4.0, there's a point there, meters per second squared. Now, let's look and see if that's what it really is. That's what the book had, but what they do is they do a lot of rounding. So let's double check. 14 divided by 3.5, and it came out exactly 4. So just to make sure it was 4. Now, the best practice, see, I'm in education, that's what we say, the best practice is to always put your units in the problem while you do it, and then look at the units and make sure that they're the same, because this was 16 meters per second minus 2 meters per second is 14 meters per second. 4.5 seconds minus 1 second is 3.5 seconds. Then you do the math on the units. If you have meters divided by seconds, this seconds is also in the denominator, so it's meters per second squared. So the best practice is to put your units in the problem and to divide them or to do the math on them. Now, I didn't do that because I figure you're looking at this on a screen and it's kind of hard to see and my handwriting's bad. I know my handwriting's bad. So I thought I would leave them out just so it looks more simple and clear. Okay, the second problem, if we were in class, I'd say, do you understand? But if you don't, pause the video and try to do it each step yourself. Okay, so the next one is this car is backing up and it's speeding up as it backs up. It's in a hurry to back up, run back in the house and get what it forgot. It's probably their cell phone is what they probably forgot. So because it is backing up, then the book calls that negative. That it is negative because its position is going backwards, so it calls it negative. I've been in physics classes where they do handle that a little differently. It's not that one's right and one's wrong, it's just different. So if you're in a physics class where they handle backing up a little bit different, just know how your class does it. However it is, that's how you substitute it in, okay? So, for example 2, we're told that the initial velocity is negative, see it's starting off backing up, so it's negative 2 meters per second. Then it gets faster, its final acceleration is negative 9 meters per second, and it did this, the change in time was 2 seconds. So I think, is there a formula that relates change in velocity and change in time and acceleration? Because that's what I want. And yes, there is. It's this one. The average acceleration is change in velocity over change in time, same one we had before, and we're just going to substitute it in. So our final minus initial is how we get the change. So negative 9 minus negative 2, what do two negatives make? That's right, a positive. So it's really negative 9 plus 2 is negative 7. And then the change in time is 2. So negative 7 divided by 2 is 3.5 meters per second. And really it should be negative because it's accelerating in reverse. So negative, I left my negative off. But all right, let's move on. Sorry about that. Try not to make y'all feel dizzy as you do this. To number 3. So example problem number 3 says that you've got this graph, and it is the graph of a sprinter during a 100-meter dash. The 100-meter dash is not important. Sometimes they will throw numbers in there to be what I call red herrings, which they're trying to throw you off, but we don't care about that because what we want is average acceleration between, first of all, between 0 and 1 second. By looking at this graph. So you go from 0 to 1 second, you go up, and you see that the velocity is here somewhere bigger than 7, but not quite 8, if you count the little squares. Well, they said it was 7.8, and I'm like, good for you to figure that out. I don't know that I can read that. So my first given is the change in time is between 0 and 1, so I do final time minus initial. 1 minus 0 is 1. And then by looking at the graph, I see, and my formula is acceleration is change in velocity over change in time. And then I just divide it. From the graph, 7.8 divided by 1 is 7.8 meters per second squared. Okay, then they want me to do it again. And this time they want to use the time between 4 seconds and 2. So you go over here, and that's 2 and that's 4. So it's these 2 points on the curve. Now I can tell that that's probably less than 1, but that's all I can tell you about that. But they boldly said that that was 0.8 meters per second. I'm like, good for you. You must have better eyes than I do. So it's the same formula. Acceleration, average acceleration equals change in velocity over change in time. They're 0.8 divided by 2, so it is 0.4 meters per second squared. All right, so those are pretty fun. And if you're taking my class, there is one like that on the test. There's one like all these problems, so make sure you always study your problems too. All right, so this is example number 4. And this one is where we are going to figure out final velocity. Okay, it says, I'll read out loud while you read silently. Or you can read out loud too. I don't care. It's just I've given the Iowa a whole bunch, and that's what you say. If a car with a velocity of 2 meters per second at time of 0 accelerates at a rate of 4 meters per second squared for 2.5 seconds, what is the velocity at time of 2.5 seconds? So that sounds like gobbledygook, so we got to straighten it out. So we're given that it's got a velocity of 2 meters per second at where the time is 0. It accelerates to 0.4 meters per second squared. The second time is 2.5 seconds. And what we want is the final velocity at 2.5 seconds. So is there a formula for final velocity? Yes, there is. And it is that's the initial velocity plus the acceleration times the time. Our initial velocity was 2, our acceleration is 4, our time is 2.5, bada bing, bada bang, 12 meters per second was our final velocity. All right, let's move right along. We're to number 5. Number 5, we have a train. We love train problems in physics. They're great, okay? What is the displacement of a train as it accelerates uniformly from, now it says positive 11 meters per second. That means it's speeding up going forward, not going back, to 33 meters per second in a 20-second interval, okay? So for problem number 5, the right problem, we want to know the displacement, the distance, and we have our initial velocity of 11 meters per second, our final velocity of 33 meters per second, and our change in time is 20 seconds. Now, this is our formula. Displacement equals 1/2 and change in velocity times time. You can write it this way, 1/2 delta VT. Okay, so 1/2 and our change in velocity is we went from, it's not change. It is our total velocity, VT, our tot. 33 plus 11, we add them. I'm so used to always subtracting. Sorry about that. Forget that happened. All right, and then our time is 20 seconds. We substitute it into our formula, do 1/2, and you could just put 0.5 and not have to deal with fractions on your calculator, times 44 times 20, and it's 440. They wrote the answer like this. They really like scientific notation. In scientific notation, you take the decimal point, you move it 2 places till it's in its proper place behind the first non-zero digit, and then you write how many places you moved it up here in this exponent. So we moved it 2, so it's 4.4 times 10 to the second power. All right, that was fun. Number 6. Gotta love the train problems. Let's go on to problem number 6. It's right here. Now we're going to calculate displacement from acceleration in time. So they tell us a car starting from rest, so that means 0, accelerates uniformly at 6.1 meters per second squared for 7 seconds. How far does the car move? So we list our knowns and unknowns. It accelerated 6.1 meters per second squared. Its time was 7 seconds, and its velocity is initial, because it started at rest, was 0. So this is our formula. Displacement equals initial velocity times time plus 1/2 acceleration times time squared. A lot of times in these problems, you don't really have to do this, because if it starts at 0, 0 times anything is 0, and 0 plus anything is itself, so that part doesn't really matter. But it's always good to write it and put it in anyway, because you're showing your work completely. So the initial velocity is 0, the time was 7, 1/2 is 1/2, the acceleration was 6.1, and time is 7 squared. Now, make sure you get these squared. A lot of times students will get it wrong because they'll forget to square. Put it all in your calculator, and the book said it's 150. I don't know if it's exactly or if they rounded off. You try it on your calculator, and you can see. All right, example problem 7. It says, so this one's an airplane problem. We love airplane problems almost as much as trains. An airplane must reach a velocity of 71 meters per second for takeoff. If a runway is 1 kilometer long, what must the acceleration be? Okay, so let's write down what we know and what we don't know. Okay, so our velocity is 71 meters per second. Our distance is 1 kilometer, but notice that that is meters, so we need to change those kilometers to meters because we need the units to work out, and the units won't work out, and you won't get the right answer if you mix units in a problem. So whatever one thing is, always make sure the other one is that, especially in college. This book isn't so bad, But when you take college physics, they will rarely give you the right units. You usually have to change them before you can use them, okay? The acceleration is what we don't know. Our initial velocity is 0, okay? So, because we're starting at rest, we're going to take off here, okay? And so we're solving for acceleration. Our final velocity minus initial velocity squared divided by 2 times the distance. You put that into your calculator, and it's 2.5. Notice then they redid the problem, and they said it would be the same thing needed if you were going the other way. If you were taking off or landing or taking off, you would still need the 1,000-meter runway. All right, example number 8. Example 8, it says that we used to have this ride at Six Flags in Atlanta. It was called Free Fall in Atlanta. In Cedar Point, Ohio, it was called the Demon Drop. Maybe they didn't think that would work too good in the Bible Belt to the south in the 80s. But anyway, it takes you up, click, 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 and then you get right here, and you look over Six Flags and get real scared feeling, and then it push you out, and you go, woo, and you just free fall down. You'd end up on your back, and then it would go back and let you out. I really liked it, but it didn't last long. But I thought it was really fun. I think it was there in the 80s and even maybe the early 90s, but then they took it out. It got real rough where it kind of hurt your back. But anyway, I get excited. I love Six Flags. I love Disney. I love amusement parks. And it's not just because it's all physics, just because it's fun. All right. So it's going to fall for 1.5 seconds. So that's a time. So we write that down. What is its velocity at the end of this time? So that's going to be our final velocity. How far does it fall? That's a distance. Okay. Now what is making it fall? That's right. Gravity. So we're going to have our time, our question marks, and then gravity is something we know. It's 9.8 meters per second squared, acceleration due to gravity. And we also know our initial velocity is 0, because remember I told you, you just sit at the top and get scared for a few minutes before they drop you. It's like that acrophobia we've got now. They scare you before they drop you. All right, so what we want is final velocity, and there's a formula for that. It's initial velocity plus gravity times time. So our initial velocity was 0, gravity, we're falling down, so it's negative 9.8, and time is 1.5. So our final velocity, we are going down, we're falling down 15 meters per second. So that's what it means by the negative. Now they want to know the displacement. Is there a formula for that? Yes, there is. Displacement or distance equals the initial velocity times time plus 1/2 gravity times squared. Initial velocity was 0, so this isn't going to matter, but we're going to put it in anyway to show our work. Plus 1/2 times gravity, 9.8, times time, 1.5 squared, and it's negative 11, which means that it's lower. You end up lower than you started. We went down, not up, on that ride. I used to really like that ride. All right. I like the gasp even better, though. That was fun. All right, our next one is a tennis ball, okay? A tennis ball is thrown straight up with the initial velocity of 22.5 meters per second. It's caught at the same distance above ground from which it was thrown. There's a little picture there. How high does the ball rise? How long does the ball remain in the air? All right, so let's look at what we know and what we don't know. Okay, so our velocity where it starts out is 22.5 meters per second. We don't know the height. We don't know the change in time, but we know gravity. We know what's going to make it come back down, 9.8 meters per second squared. Do we have what we're looking for, first of all, is how far did it go? Did I write that down yet? Yep. Okay, so we have a formula for that. The displacement is the negative initial velocity squared divided by 2 times gravity. So it is negative 22.5 divided by 2 times negative 9.8. The two negatives cancel out, and you get 25.8 meters. That's how high it went up. Second, we want to know what is the time. So D is h. The distance is the height. So the next thing is the time. Do we have a formula for that? Why, yes, we do. It's negative initial velocity divided by gravity. So it's negative 22.5 divided by negative 9.8. The negatives cancel out and you get 2.3 seconds. And time can't be negative. We can't go back in time, no matter what the sci-fi things say or what the doctor can do. Regular people can't. So time can't be negative. All right, example 10. We're finding the displacement when velocities and times are known. A spaceship far from any star or planet accelerates uniformly from 65 meters per second to 162 meters per second in 10 seconds. How far does it move? Okay, so we're given an acceleration. The initial acceleration, we're given its final acceleration, we're given its change in time, and we want to know displacement. Do we have a formula for that? Why, yes, we do. It's 1/2 final velocity plus initial velocity, that's what I wrote wrong last time, times time, but you forgot about that, remember? I told you we're forgetting about that. All right, so we add up our velocities right there. We multiply them times 1/2 and times our time, which was 10, and got the answer, 1,140 meters. And then they changed it to kilometers, even though the problem didn't tell you to, which I think is irritating. I like physics books that say, state your answer in kilometers, then I know to change it. But they just sort of sometimes change it and sometimes they don't. But anyway, it's a better physics book than I could write, so I shouldn't complain about it so much. Okay, I think that's our last problem. Let me make sure. Yes, it is. So practice all of these on your calculator. Stop the video, go through it, practice them, make sure you can do them. I think they're pretty fun. You just got to know the formulas. If you're taking the class for me, your test will be open book, open notes. So you'll be able to look back at example problems and you'll be able to look back for formulas. I don't make you memorize formulas. This is the technology age. I figure you can look them up. And the more you use them, you start memorizing them eventually. All right. So science is great. Like, share, subscribe, and I will see you next time.